Okay. Okay. So we were talking about minimizing the RSS from by choosing the coefficients beta 0 through beta d. And we went through one derivation where we did this and we got this expression, but this one is not very interpretable. So we're going to do it using slightly different approach where we split the intercept off from the remaining slope coefficients and we treat them a bit differently in the derivation. And then the other thing is, in order to do that, we had to talk about sample statistics. So we have the sample mean and the sample variance described for scalar quantities, also the sample covariance for scalars. And then we did the same thing for vectors. So we have the sample mean for vectors. The variance generalizes to the autocovariance matrix and the covariance to a cross covariance vector for us. So for example, this cross covariance vector is the covariance between each one of the features in our training set and the targets. Okay, so the last thing we did was we came up with a slightly different expression for the autocovariance. First, what we did, we just basically expanded this, and then a couple terms canceled, and we got this expression. So here, what we're doing is we're subtracting the mean before we do that multiplication. And here we're not subtracting the mean in this part, but we're subtracting the entire outer product mean matrix later. And then we did the same thing for the cross covariance to get this expression. And as we'll see, these expressions are more likely to arise in derivations. Okay, so so finally getting now to the derivation of minimizing RSS. So we take our RSS expression, which is this, and we take the partial derivative with respect to the intercept coefficient, and we try to figure out what value that coefficient sets it to 0. So here, what we did is we looked at taking this derivative. We can move this partial derivative through the sum because of linearity. And then we use chain rule. So you get 2 times this whole thing times the partial derivative of this expression with respect to beta 0, which is just going to be -1. And so that minus shows up here. And this is an expression that has to hold to satisfy this equation. And then the other thing is we want the partial derivatives with respect to all the slope coefficients to also be 0. So we did a similar thing looking at that derivative. In this case, we again move this through the sum. Then we use the chain rule. So we get 2 times this whole thing. And then we multiply by the partial derivative of this with respect to the jth beta. And since the jth beta is inside this expression, we expanded that expression into a sum over a new variable j prime. And so we can see that only one of these j primes will match this j. And for that particular value of j prime, this is what remains of the sum. All the other terms they go to 0 when you take the derivative. So finally, when we take the derivative of this respect to beta j, we get xij. And we have a minus here, so we have a minus xij. Okay, so that's where we were at the end of our last meeting. And so now we can proceed with the derivation, simplify things a bit. So let's start with this expression. And let's multiply, actually, this is the whole equation here. Let's multiply both sides of this equation by -1/2n. That does not change the 0 at all, but it simplifies this to +1/n. Okay, so then we get this expression. And the reason we did that is we can see that we're probably going to get some things that look like sample statistics, like sample mean and so on. So we can now expand this this product, and we get this average of the yi, first term, and then we get the average of the minus beta zero, which is just minus beta zero, and then we get the average of this last term, which is here. And finally, we can recognize this average of the yi's as y bar, the sample mean, and then this average of the xi vectors is the x bar sample mean. So last step is to move this minus beta zero to the other side, in which case we get this equation beta zero equals y bar minus x bar transpose beta 1 through d. So that is one of the equations that has to hold true for one of the equations that has to hold true for our coefficients. Now this tells you what beta zero should be based on all the other slope coefficients. We don't know those yet, so that's the next step. Any questions so far? Okay. All right, so let's move on to minimizing RSS. So this is the other expression that we derived over here after we multiply both sides of this by, again, 1 over minus 2n. We get this expression here. And now we similarly expand this out. So we get the average there. We get the average of xij times beta zero, which is x bar j beta zero. And then we get the average of this vector inner product, which gives us this. And then the next step is to take our beta zero expression and plug that in here for beta zero. And what's going to happen there is that is going to split this into those two terms. You can see that there's the y bar, and you can see here x bar transpose beta 1 through d. And finally, we're able to see some things pop out of the equation. But just one last step. This is all a scalar expression, right? This is scalar zero. These are all scalar terms on the right. But you can also think of xij as the jth term of the vector xi. This is the jth feature in the sample vector xi, the ith example of the training features in the data set. So this is another way to write it. We can take this scalar, write it that way, or we can say this is this vector jth entry. So we've done that here. Similarly, we've done the same thing here. We can also say that x bar j is just the jth entry of the x bar vector. And that's what we've done there. And so putting those together, you might notice this. Let me ask, is Alex Rizzoni here? Can you tell us what is this thing down here? Can you unmute yourself, Alex? Okay, not getting anything from Alex. What about Nils Sommerfeld?
I'm here. Also, it looks like Alex doesn't have a mic that I can answer if you want me to.
Okay, yeah, I see that his mic is turned off, but
Oh, he said in chat that he doesn't have a mic. So,
oh, let's see. Okay, let's see. I should open the chat window. Okay. All right. So Nils, do you recognize what this expression is?
it looks to me like the covariance or SXY or something like
exactly. So
that.
it's the vector SXY. And then we have something else going on here. Let me ask let's see, Eric Wang, do you see what that's going to be? All right. Not get anything from Eric Wang. What about Wes Water Street?
Eric also answered in chat.
Okay. So yeah, you guys got to have mics when you use Zoom in our class. So this over here, this is the autocovariance. If you remember, negative autocovariance based on our expression. This and then because of this minus. So over here we have a minus SXX, and then that gives us overall the expression is going to be SXY minus SXX matrix times beta 1, 3D. And this is the jth entry. Okay, so we now know that the jth entry of this vector needs to be 0, but we also know that this has to happen for all j through 1 through d. So that means that this entire vector is really the 0 vector. And as the last step, how can we figure out what the beta 1 through d is? Let's see, is Zach Herman here? Actually, I don't see Zach Herman here.
Can you hear me? Yeah, I'm here.
Oh, you are. Okay.
I'm not sure.
Okay. So it's
Oh,
just it's just basic linear algebra. If you have a linear system of equations like this, we can bring SXX to the other side. Equals SXY. And then now we multiply both sides of the equation by inverse of SXX. And we get the expression for beta 1 through d. And this is assuming that this inverse exists. We'll talk more about that later. So basically, we have solved the problem we set out to solve. So this is our expression for beta 0 we derived. Oh, and yeah, so this was beta 1 through d. We just plugged in the expression for beta 1 through d. So this is what we have for beta 0, and then this is what we have for the remaining slope coefficients, and we just stack them vertically into this column vector. And so we basically have this. This is a scalar on the top and then a vector below it. Okay, so this is the least squares solution. We've derived that. And there's a special case of this, sometimes people consider, where you either have only a single feature or you choose to use only a single feature. So d equals 1. And in that case, all of our vector quantities turn into scalars. So our vector of features for the ith sample turns into a scalar. The mean vector turns into a mean scalar, and so on. This covariance matrix turns into a scalar variance, and this vector turns into a scalar. And so in that case, if you make all those replacements there, you get the quantity y bar minus x bar times SXY divided by SXX on the top, and then on the bottom coefficient is SXY divided by SXX. And this is just a vector with two coefficients that are the least squares coefficients. One, the slope coefficient for the feature you're using, and then the intercept. And something interesting happens if you normalize your data so that you subtract the mean from all your labels and you subtract the mean from each of your features, you'll find that these mean quantities are both zero. And if you plug in those zero values, the beta zero coefficient also turns into zero. So this is something that we don't necessarily need to do, but it is a good idea to do it when you're using regularization, which we'll talk about in Unit 4. For now, it's optional, but if you do it, you do this normalization, then you'll actually get a zero for your intercept coefficient. Okay, any questions so far? Okay, great. So that's the least square solution. So now let's turn our attention to understanding whether our least square solution is good or bad for the data set that we're using. And what we're going to do, we're going to come up with a particular number, which is a measure of goodness of fit. And basically, to understand it, I think it's easiest to think of a normalized version of RSS. And the reason why RSS alone is not very useful is if you think back to the RSS expression, you can see that it sums over all your training samples, which means that as you have more training samples, the RSS gets larger. And so that means that a large RSS is not necessarily bad. It just might reflect the fact that you have lots of training samples. So a sensible thing to do is to always divide your RSS by the number of samples, and then you get a sample invariant quantity, which tells you, in a certain sense, how well you're doing. But there's one other issue, is that the RSS depends on the variance of your training labels, this SY squared. So maybe in some data set, you happen to have, someone gave you the data in some units that made the Y values large, and now their variance is also going to be large. And so that is also going to make the RSS not really interpretable. Even this normalized RSS is not going to be very interpretable. So as one further step of normalization, you can also divide RSS by the sample variance of your features. And at that point, the thing that you have is normalized quite well. And that would be good enough, except that it's not what's typically done in the literature and statistics and so on. They look at 1 minus that quantity. So it's 1 minus this normalized RSS. And this is known as R squared, the coefficient of determination. So it's just, this is a sensible thing we could use, but instead we're going to use 1 minus that. And so let's take a look at the kind of values that you might see or can expect to see. So the best case situation is if you can predict your training labels perfectly. In that case, your RSS would be 0. And so this whole thing here would be 0. And that's actually the lowest RSS can ever go negative. So the best case R squared is the value 1. And that is what you get for perfect prediction. Now in practice, we don't expect that to happen in most cases. So we expect to get an R squared less than 1. But the next question is how small can R squared get? So one idea we can think of is what I call the trivial predictor. And what the trivial predictor does is it ignores the features entirely. It just says, I'm not even going to look at the features for prediction, but I am going to use the labels. And what I'm going to do is my prediction for every training label is just going to be the average value of all the training labels. So if we call that the trivial predictor, it turns out that this gives an R squared of 0. So it's sort of like another extreme. It's in some sense the worst case extreme for a sensible predictor. And by worst case, I mean maybe the training features that you were given tell you nothing at all about the labels. So no amount of prediction is going to help. And so you might, in that case, see something like R squared equals 0. So that's sort of the worst case for a sensible predictor. Now, it is possible to get a negative RSS if you use just a poorly designed predictor. You can definitely get something that's arbitrarily, negative. So worse than trivial. Okay, so that's just something to keep in mind. So when you do an experiment and you look at the training R squared, you can interpret how well your prediction is working. And that can be maybe a debugging aid. If you notice that you're getting like an R squared greater than 1, that's impossible. Or if you're getting an R squared less than 0, it means either there's a bug or there's probably some bug in your code if you're trying to do least squares prediction, there's a bug and so on. Okay, any questions on RSS? Okay, so great. So let's talk briefly about how we implement this stuff in Python. So there's several options here. The first option, which is not a recommended option, but it's possible, is to implement this expression that we derived first. So in this expression, in order to implement this, you would first need to construct your A matrix. And assuming that you have your X matrix, this is usually something you get when you download your data, you can construct your A matrix by first making a column of ones. And so we can do that using the numpy ones command. Here we're telling it, we're making that one matrix the right dimensions. And then we can use HStack to make this matrix A, where we do this horizontal stacking between those two matrices. And then finally we can, or not finally, but the next thing is we can implement this A transpose A inverse. So in NumPy, the @ sign is the matrix multiply, and the .t is transpose. So here we're doing our A transpose A, and then for inversion, we can run this function. And then finally, we can multiply that times this using this dot product. There's different ways to do it. You could also use an @ sign there. So at the end of the day, you would get your beta coefficient vector. The trouble with that is that it's not the most efficient technique in terms of the numerical linear algebra, because you end up wasting kind of unnecessary computations building this matrix and inverting it and so on. So there's a smarter approach, which is to use the least squares command within the linear algebra library of NumPy. And this uses some numerically efficient linear algebra routines and gives you the same, more or less the same coefficients. I say more or less because there can be some numerical robustness issues. Sometimes this inverse, if the matrix is ill-conditioned, the inverse can give you weird numbers. This is actually going to be more robust. And so this is a preferred technique, but it's still not the thing that I would recommend using in this course, because we have this package or library sklearn, which is the Python basic machine learning library. And it gives you an alternate way to do linear regression, or this least squares linear fitting that we're talking about. And the way that it's done, it takes a couple steps, but it's basically the way that sklearn implements all of their different functions. So when we learn how to use it here, we're going to be able to use basically the same approach when we do classification and many other machine learning tasks. So the way that we do this in sklearn is first we import the linear model function from the sklearn library, and then we instantiate a linear regression object. And an object is really, it's a collection, it's a container that has a collection of different places for storing variables as well as different functions. And so once you instantiate it, you basically set it up, and now you can get access to its functions. And so what we can do next is we do regression.fit. So we call the fit function in that object, and now we have to give it the training data. So we give it the X matrix and the Y vector. And when we run this internally, it computes the beta coefficients and stores them. It stores them internally. It doesn't spit them out unless you ask for it to do so. And now that those are stored internally, when we want to do prediction, if I say predict the labels associated with this matrix X, because this is the training matrix, it's basically going to predict the training labels. And so that's how we can, do prediction in sklearn. And the last steps are just going to be evaluating how well our prediction worked. So here we have our y hat vector. This is the true vector of training labels y. We can subtract them, we can square them, and then we can take the mean of that vector. Doing that gives us RSS over n, which I am calling normalized RSS here. And then to get r squared, remember it's 1 minus normalized RSS, but then also divided by sy squared. So this is the standard deviation squared as a variance. And so this is going to be my r squared. And so for this auto mile per gallon demo that we've been working with, the r squared ends up being, about 0.71. So now we have an interpretation of how well least squares is actually working on this data set. So let's see, Spencer Munch, would you say that least squares is working well or not well, or what?
I don't have a ton of experience engaging this sort of thing, but
Well,
I
you
would
don't
say
need any
it's
experience because we just talked about it. So remember, this is what we have.
yeah. Well, I just assume that since it's closer to a value of 1, it's going to be moderately accurate.
Yeah, exactly. So this gives us like just a normalized way of looking at things. So the closer our prediction is to 1, like the more perfect it is, and it's a bit closer to 1 than 0. So I would say in this case it's probably working relatively well. It's not like it's completely failing on this data set. And so that's the interpretation that we have. Okay, any other questions on computing the solution or interpreting how good it is? Okay, if not, then let's move on to talk a little bit about simple versus multiple linear regression. So if you remember, simple linear regression is where you have a single feature you're using for prediction, and multiple linear regression is where you have multiple features. So here we have a single feature X, here we have D features. And so the question is, if you're given a data set that has a bunch of features, like I can't remember exactly how many this data set has, maybe like 8 or 9, you could use all of them, or you could just choose to use one alone. And you could choose which one. So what do you guys think? Like, what's going to be better? Is it going to be better to use multiple features, or is it going to be better to use a single feature? Someone said more. Does anybody have some other ideas? Is it always, okay, another vote for multiple? Does anybody think that maybe more is not always better? More to extent, depends on the model. Okay. So it's a little bit of a trick question because I haven't given you enough information to really ascertain whether it's good to use one or more than one. It turns out that in machine learning, sometimes if you have too many features, they can actually act as noise in a certain sense. And it could actually be good to ignore them. However, we actually have to think about what is the goal. So if the goal is to minimize our training error, then it is definitely better to use as many features as possible, to use all of them. If our goal is to not focus on the training error, but to do a good prediction on unseen data, sometimes you call that test error, in that case, we might benefit from using less than all of our features. And we will actually talk about that second case in the next 2 units. So for now, if all we care about is minimizing RSS, we definitely want to use all of our features. Using single feature, any of them is going to be worse. And we can see that in a little experiment with this auto MPG demo. We have a little for loop here. And what it does is goes through the features one by one, and it prints out the R squared if you use, let's say, the J = 0 feature alone. we start always counting with 0 in Python and NumPy, so that's why it's 0. So for example, if you use just j equals 0 feature alone, the r squared is 0.65, which is actually not bad, but if you remember, we could do better. We got 0.71 if we use all of them. And then if we use j equals 1, that feature, we get 0.61. If we use j equals 2, we get 0.69 and so on. J equals 3, not as good. We're only getting 0.18. So, you can see that none of these are as good as using all the features simultaneously. And here we also can see the values you get, the different size of the beta 0 intercept coefficients and the different size of the slope coefficients. So they can vary depending on the feature you're using. But the moral of the story is multiple linear regression will give training RSS at least as good as simple linear regression, usually better. Okay, any questions? Yeah, there's a question here. If there are too many parameters, can we overfit? Yeah, that's exactly the idea. So to understand what exactly we mean by that, we have to define what is overfitting. And that's exactly what we're going to do in the next unit. So I'll just postpone that idea until the next unit. But right now, like overfitting is really, it's the question of if I have this training data, I can maybe do well on that, but then I'm not going to do well on test data necessarily. That's where overfitting shows up. So we'll get into all those details in the next unit. Okay, any other questions on anything we've done so far? Okay. So just maybe to think about this a little bit more, sometimes we can make a distinction between training and testing data. So, and we can even do that with a single data set like this one that gave us 392 samples. We can sort of construct two different folds of data. One, we'll take, a random 300 samples and we'll use that for the training data. And then we'll take another random, the remaining random 92 samples, use that for test data. And what that means is we make separate quantities like X train, Y train, X test, Y test. And then when we go to do the model fitting, we use the training labels and features. When we do prediction, we can do prediction on the training labels, but we can also do prediction on the test labels. So we get two different, this has 300 predictions on it, and then the other one has 92 predictions. And then we can compute R squared for each of these. And when you do that, you notice that we get, again, 0.71 for the training and 0.68 for test. So let me ask, is Eric Jackson, what do you think? Is this kind of what we would expect? See, is Eric Jackson here? Maybe not. What about Emily Weigel? See, Emily, I saw you here before.
Yes. Can you hear me?
Yes. So what do you think? Is this kind of what we would expect or not? In terms of these two values?
Yeah, because there's so many samples.
Do you think does the test always have to be lower than training?
No.
Yeah, not necessarily. Usually the test R squared is going to be a little bit worse than training because when the goal is to match the training data and we use the training data to achieve that goal, we're very well matched to the goal of maximizing training RSS, or training R squared. But when we train on the training data and then we apply that to the test data, we expect maybe to do a little bit worse because we've never seen that data. It is possible to get lucky and do even better on the test data that we haven't seen, but I'd say it's pretty typical to get an R squared that's a little bit lower. Okay, so we'll discuss all this a bit more in the next unit. Okay, any last questions on training versus testing or anything like that? Okay, let's move on to the very last topic of this unit, which is categorical variables. And what we mean by categorical variables are, as an example, what if you want to predict the miles per gallon of a car given horsepower and brand? And the brands are something like Ford, Honda, BMW. So the issue here is that we need to turn Ford, Honda, BMW, the categories, we need to turn them into numbers in order to use something like NumPy. And the question then is, how exactly do we do that? So you might say, well, I'll just assign Ford to feature value 1 and Honda to the same feature value 2 and BMW to 3. But this doesn't always work well. Does anybody have any ideas of why not? Feel free to unmute yourself if you like. Okay, so why doesn't it work well to just assign numerical values to brands?
Is it because they have weights instead of like indexing?
Well, I would say it's because when I say Ford is 1 and Honda is 2 and BMW, it's like I'm applying some ordering to those that somehow like Honda is better or bigger than Ford and BMW is bigger or better than Honda, right? And it's not really clear that that's the right kind of ordering for the problem you're working on. So if you end up doing this, you kind of bring in some kind of weird bias that is probably not going to be what you want to do. You'll get an answer, but it's going to be affected by the exact numbers that you choose for the different categories. So we want to come up with a way of coding the categories in a way that is like very fair and equal in how we do that. And so the common solution to this is to use something called one-hot coding. And that is to represent brands or categorical variables by one-hot vectors. And so what we mean by that is you take what used to be this scalar x2 feature variable, and you actually expand it into a set of 3 variables, because we have 3 brands in this case. And then you assign the vector a one-hot vector, meaning a vector of all zeros, except one value is 1. So Ford gets for those 3 new features 100, Honda becomes 010, and BMW becomes 001. So at this point, when you do your linear regression, you actually have now 4 features, 4 scalar features. You have X1, and you have these new 3 different features, which altogether you're using to encode the brand. So is this idea clear, or are there any questions?
I guess in say you have a categorical variable, or I guess if you only have 2 states, I think in the homework number 2, it was asking about including gender as a categorical variable.
Mhm.
And so I'm kind of curious as to how adding multiple categorical variables like x's 1 and 2 and 3 versus just establishing one as a baseline in the case of a kind of like a dualistic
Okay.
categorical variable.
Well, yeah, so we'll talk about that on the next slide. The case where you only have 2 is a little bit of a special case, which I think you'll understand in a moment. But for now, let's just say, let's not look at that special case and say you have 3 or more. So let's
Okay,
say if
got
you
it.
have 3 or more, is this idea clear enough? Like what we're doing? Is it clear? Okay, so no question. So hopefully it's clear what we're doing. So this is going to be our new linear model. As you can see, we have the original X1, which is it's called an ordinal. So let me clarify this. So there's two kinds of variables. There's categorical versus ordinal. And ordinal numbers are ordered, like the numbers 1, 2, 3. There's a clear order. 1 is smaller than 2, 2 is smaller than 3. Categorical variables are just fundamentally not ordered in any way. They're different, but you don't want to impose an ordering on them. So here, the way we're handling them is we have expanded the X2 feature into 3 new scalar features, and we assign them one of these one-hot vectors. And so now we're going to have an intercept coefficient, and we're going to have 4 slope coefficients that we need to fit. So now that's what we're doing. Now, what's actually happening, let's look at that. And I think this provides a lot of insight. So if you consider all the samples that are the forward samples, in that case, this is always going to be 1, this variable, and these are always going to be 0. So for all those forward samples, basically beta 3 and beta 4 are not in the picture. And X21 is always 1, so that's not in the picture. So for all the forward samples, they have a structure like this. So they're going to have different X's and Y's, but they all look like this. Now for the Honda samples, it's similar. You get 0, 1, 0. And so essentially you just have the beta 3 there. And then for all the BMW samples, you just have this beta 4. So now when you look at it, you can say, oh, okay, this is what's actually happening. For the forward samples, you have 2 different intercept, or actually you could say you have a sum of intercept coefficients. For Honda, you have a possibly different intercept coefficient than you can fit. So when you do this kind of one-hot coding, you're essentially allowing a custom intercept for each brand or for each category. So that is what's happening. Is that clear? Any questions on that? Okay, so this is actually not the only thing you can do. This might make sense if you think, there's not like any single intercept beta 0 that can really fit my data, all my data, because my data, it has really there's 3 flavors of it. There's the Ford data, the Honda data, the BMW data. And so in some cases, you might say, I just need to use a different intercept for each one of these categories of data. But in other cases, you might say, no, the intercept, it should be the same. I should actually get to use a different slope variable for each category. And we can do that too, just by using a slightly different version of one-hot coding. So what I describe here, you can say this is one-hot coding of intercepts. And now we can talk about one-hot coding of slope. And so again, the one-hot coding part is the same. We're going to have these one-hot vectors expanding according to the number of categories we have. But what's going to be different is how we use them. So now what we're doing is, this is our ordinal feature. You can see that we are having that in common, but we're taking the product of the different categorical or one-hot variable there. And so now when you go through the same exercise of saying, what happens with all the forward samples? They all look like this. What happens with all the Honda samples? They all look like this. And notice that the forward samples all have beta 1 for the slope coefficient. The Hondas all have a beta 2. And the BMWs all have beta 3. And this might make sense if you say I think Ford, they have this particular definition of horsepower where they measure horsepower a little bit differently than Honda does. And so in order to really fit my data properly, I have to allow a different slope variable for all my Fords versus all my Hondas versus all my BMWs. And so this is definitely an option you can do. You can do one-hot coding of intercept. You can do one-hot coding of slope. You just have to make that choice, in order to do the fitting. Okay. Is this making sense, the one-hot coding of intercept and slope? Any questions? Okay. You can in fact do one hot coding, combined intercept and slope, but at that point, what you're doing is you're doing a completely separate fitting of all the Ford samples. You're just looking at the Ford samples and fitting slope intercept on them, and then separately you're looking at the Honda samples. And the issues with that is that sometimes if there's a sort of a connection between the slope coefficients, it's in our advantage to use more data. If the slope coefficients really are the same across categories, we'll get an advantage to using more data. And we'll see exactly why that is in a later unit. But you get something out of using fewer numbers to model data if that's the appropriate choice. If there's no single number that can fit your data, then it's better off to split it and to do a data dependent fitting or category dependent fitting. Okay. Would you ever have multiple instances of one hot coding, like if you took brands and say car type? Yes, exactly. So you could have multiple categorical variables, in which case you sort of need to do some combinations of one hot coding of whatever different categorical variables you have. So you can see that doing this thing, you end up getting more and more features. Features start to expand, but that's definitely what happens when you have several categorical features. Any other questions? Okay, great. Now there is a bit of an issue with what I said. One hot coding the intercept can make this matrix A transpose A non-invertible. And that's the matrix that we said needs to be invertible to compute our least squares solution, at least in the typical way. And let me explain now why this is. Essentially, it's like when you have, when you're doing intercept only one hot coding and you're using the scheme that we talked about before, you end up getting more variables than you need. So like here we have 1, 2, 3, 4 different variables that we're using to model 3 intercepts. So there's a redundancy there that is going to hurt us in the sense of making a certain matrix non-invertible. One way we can see this is our equation again that we have in this case. And if you think about the rows of this matrix, they will either, the rows of the A matrix, they will either look like this anytime you have a Ford sample, like this anytime you have a Honda sample, or like this anytime you have a BMW sample. And it's possible to find kind of a strange vector like this beta vector, where we have 1s here for all the slope coefficients. If you look at this vector, and we've also, we've basically found some beta vector that gives, no matter what row the matrix is, it's going to give us 0 for the prediction. So basically what we're doing is, because this times this is always going to be 1, and this times this is always going to be -1, they cancel, and then I have a 0 multiplying the only thing that has some variety over my samples. And so whenever I use this beta, I always get a 0 prediction. And remember that if you can find a beta vector such that you multiply a matrix to get 0, and this is a non-zero vector, it means, actually, sorry. If this is true, we can multiply on the left side by A transpose, and this must also be true. And finally, if there's a non-zero beta such that that equals 0, then the matrix must be non-invertible. So this is just like a little proof of why it's non-invertible. And the solution to this problem is just get rid of one of the columns. You don't really need to use 3 columns. In fact, if you do use 3 columns, you run into a problem. So you can remove any one of these columns in the one hot coding. And for example, if you remove the third one, you get this. And now you're using 3 different slope parameters to model 3 different intercepts, or sorry, 3 different intercept parameters to model 3 different things. And this solves a problem. So coming back to the question that was asked a few minutes ago, what if I only have 2 categories? Well, that means that if I use 2 airy one hot slopes, I run into trouble. So I get rid of one, and now I'm down to 1 category. And at this point, it's like for all the Ford samples, you would, use a number like 1, or actually any number, and all the Honda samples, you would use 0. So that's kind of what simplifies in the case of just these binary variables is one hot coding. You just need to add like one number that codes the difference between your two categories, and it can be really any number. So hopefully that answered the question. Are there any other questions about one hot coding? Okay. If not, we just have one more slide, which is kind of an introduction to the next unit, but also a realization that even though it sounds like the model we've been using is very kind of weak because it's only like using linear functions of our features, you can actually do a lot of cool stuff by doing some nonlinear processing of features to make much more interesting feature sets. So for example, if we had a single variable x, we could do linear regression, which would only basically be using this model. Or you could say, well, why don't I add a new feature, which is going to be x squared and then x cubed and so on up to x to the power d. So this is now giving us what's called a polynomial model. And now I have a much more sophisticated way to do prediction. I have more coefficients to fit, but I can fit much more complex data sets. And the key point is that you can think of this, if you want, as nonlinear in the features, but it's linear in the parameters, which means you can use exactly the techniques we've learned in this section. This is actually a form of multiple linear regression just by defining x sub j as x to the power j. So that means we can use, all the techniques we learned in this unit. We just have to do a little bit of pre-processing beforehand. And the polynomial is just one option. You could use any nonlinear function and get some interesting things. Like you could use a cosine of x with different frequencies. So this is just all different ways to do feature transformation, which is really powerful. And it turns out that the sophisticated neural networks and deep neural networks and stuff that are in vogue now, one way you can think of them is they are doing clever things to come up with powerful feature transformations. And then at the end of the day, they're just doing linear in the very last layer. That's essentially what's happening. So, so even though it might seem like what we've done is kind of, weak and not that impressive, on the other hand, it's the foundation for everything that's done. It's just you have to use some powerful feature transformations in advance. That leaves us with only one more question, though, which is, if I'm going to do polynomial, how do I know when to stop? Like I can keep taking d larger and larger. I can keep adding more and more features of higher and higher powers. Is that necessarily good? No, probably not. You're going to have to figure out when to stop. And that is a question of what we call model order selection. And it involves overfitting and underfitting and all that stuff. And that's going to be the introduction to what we'll talk about next time we meet, Wednesday. Whether we'll be in person or online, I guess we'll see. But in any case, that's all we have for today's lecture. So I will pause the recording. But if any of you guys have any questions on the class content, you can